So let's put together some more facts, some more information to help us with sketching a graph. So if you'll recall from previous sections that we discussed that the local maximum or minimum is a maximum if you can find some small interval, so it's the biggest value. It's a local minimum if on some interval you can find a minimum value. And our number one test for finding local max and mins is the second derivative test, where we have a critical value. So the derivative is 0. And if the second derivative is negative, well, then we know that that it's concave down, right? So if the second derivative is negative, then it's concave down, and we have a max. And if its second derivative is negative, then it's concave up, and we have a min. If the second derivative is 0 or doesn't exist, then the test is inconclusive, and that's what gives us the first derivative test. If we can't use the second derivative test, we can go to the first derivative test and just compare. Well, was it increasing before and decreasing after? Then we've got a max, right? In this case, was the if before the critical value is increasing and then after that it's decreasing, it must be a max. If on the other hand it was decreasing and then increasing, it must be a min. If it doesn't, then we have something like that, where it's not a max and min, or possibly like that, where it changes concavity maybe, but it is not a max or min. So we've got a lot of facts on the table, a lot of if you will, not problems, but tools. So let's put all that information together into one strategy for graphing a function. Sorry, before I do that, let me define one more piece of information, the inflection point, which is just when the graph changes from one concavity to another. So our strategies for graphing a function using all of the tools that we have at our disposal, including the ideas we have from previous courses. Where does the graph cross the x-axis, y-axis, those kind of information, as well as the calculus information we can use. When we go to sketch the graph y equals f of x on some interval a to b, then we first compute both the first and second derivative. Since this will give us information about increasing, decreasing, as well as max and mins, this will give us information about concavity as well as max and mins. So we compute the first and second derivative. That's always going to be our first step. Then we'll find the points where the derivative is 0 or doesn't exist. Those are our critical values, and create a sign graph like we did in the exercise. Then we'll find all the points where the second derivative is 0 or doesn't exist and create a sign graph for it, just like we did in the last example. Then we'll evaluate the function at these critical values and where the second derivative is 0, and we'll plot these points. Well, why do we do that? Well, because at all the critical values, that's where we can have local max or local min. So those are going to be important spots. And then where is the second derivative equals 0? Well, those are important spots as well, because that's points where we have points of inflection, changing from one shape to another. Then, using all this information we've gathered together in the previous steps, we graph the function itself. We plot its graph. So let's do an example. So we'll look at the function y is equal to negative x cubed plus 12x minus 12 on the interval from -3 to 3. So step 1, compute all derivatives. So dy dx is -3x squared plus 12. And the second derivative is negative 6x. So now we've got our first and second derivative. Now we will, we need to determine where this is 0, and so I'm going to break this up into two sides. So we need to determine when this is 0. So negative 3x squared would be equal to negative 12. X squared is equal to 4. So we've got x being equal to plus or minus 2. So making our sign graph for f prime. Our lower bound is negative 3. Then we've got a critical value at negative 2. We have another critical value at 2, and then our endpoint at 3. Now, so we want to determine when it's positive or negative, so we'll have to take some values in between. Now, because it's not 0 at negative 3, right, it's an endpoint, but the derivative is not 0 there. So I can actually use this as an evaluation point. I can also use 0. That's a nice number between negative 2 and 2. And then again, I'm going to use 3, my endpoint. Yes, it's an endpoint, but I know my function's defined further on, and I just want to know, is the derivative negative or positive? And so if I put negative 3 into my function here, I get a 9 times 3 is negative 27 plus 12, so that's definitely negative on this interval from negative 3 to 2. If I put a 0 into my function, I get a positive 12, so it's positive on this interval. And then from 2 to 3, again, I can put 3 into this interval, and I get a negative again. So it's negative in this interval. So we can say, kind of putting this together, that my graph has to be decreasing, then it's going to have to be increasing, and then it's going to be decreasing again. Right? I've gathered that information. I know that's true about my function. So if I come back to the second derivative, so this was part step 2. Step 3 says find out where the second derivative is negative. So negative 6x is 0, which tells me that x is 0. So that's going to be a point of inflection likely. And so I make the sign graph of f double prime. So I'm looking at f double prime sign graph. And again, I'm going to go from negative 3 to 3, since that's my domain. And my one critical value, or 1, 0 for the second derivative, is at 0. So again, I'm going to pick some values in the interval, so make life easy. Let's pick 1 and 1. Sorry, this should be negative 1. So negative 1 and 1. If I put a negative 1 into the second derivative, right? So now I'm putting, this is the sign graph for f double prime. So if I put negative 1 into the second derivative, I get a positive 6, so it's positive in the interval from negative 3 to 0. And then if I put a 1 into the second derivative, it's negative, so I get a negative second derivative in there. And what does that tell me about the graph? Well, it says, okay, it's concave up, so the shape has to be something like this. And here it's concave down, so the graph has to have a shape like that. So putting this together, let's sketch the graph of our function. But before I start, so not before I start, but the first thing I need to do is get some anchors. So where are good places to evaluate my function x? So I know where it resides on, in space. So the key spots are going to be, well, what are the values at the endpoint? So at negative 3. What are its values at internal critical values, so that's -2 and +2, as well as what's its value at points of inflection, which would be 0. So I'm going to make my list here. I've got -3 is my endpoint, -2 is a critical value, 0 is a point of inflection, 2 is another critical value, and then +3 is an endpoint. So putting that together, if I put -3, so let's just remind ourselves what the function is since it's written way above. It's negative x cubed plus 12x minus 12. And if I put -3 in there, I get a -21. If I put a -2 in there, I get a -28. If I put 0 in there, I get a -12. If I put 2 in there, I get 4. And if I put 3 in there, I get -3. So I can see that here's my maximum value, -28, and it happens on an interior. Here's my minimum value of 4, and it happens on in the interior again. So I'm going to not quite do this to scale. Let's say this is the value 5, and this is the value -30. Right, so clearly it's not to scale, but I've labeled my axes so we know where the values are. At -3, it's so let's say that this is maybe -20 and -10. So and we'll do 1, 2, 3, 1, 2, 3. So at -3, it's a value of -21, so that's right about here. At -2, it's a value of -28, so that's right about here. At 0, it's a value of -12, so that's right about, so this is 10, so this is somewhere around here, is -12. At 2, it gets a value of 4, so that's somewhere around here. And at 3, it's a -3, so that's going to be somewhere around here. And we know, so let's plot our kind of our tangent lines. So we know that the slope is negative through here. It's 0 here. It's going to be a positive slope here, 0 here, and a negative slope here. So we have that information, and we can put this all together. Where's our point of inflection? Well, it changes here. Remember, 0 is our point of inflection. So our graph will go from concave up, shaped like that, and here it'll switch and be concave down. Putting this all together, our graph has to be concave up from here and decreasing till at here, then it's increasing. And now at this point it changes, but it's so subtle, it's still increasing, but now it's concave up and then concave down. Well, sorry, concave down here, concave up here, but it's increasing, then decreasing. And so this is the general shape, the sketch of the graph y equals -x cubed plus 12x minus 12. And it was all just using the derivative and the second derivative and plotting a few key anchor points. But this is exactly what the shape has to look like. Now, if you plotted this on your graph, it would look a little bit different because notice my scale is way off. This should, if we put this to scale, this height is way down here, but it'd be hard for us to see in this graph. So I just changed the scale to work. So in the next video, we'll do a couple more examples.